Hello Math 4411 students, here's Lesson 12, Integral Domains. Previously in Lesson 11, we studied rings and fields in general. Especially for general rings, we went through several subcategories. Among those, we went through integral domain. Do you remember the definition? An integral domain is a commutative ring with unity with no zero divisor. No zero divisor. That's the key, and that's the topic for section 1. Let's study that. What do you mean by zero divisor? And what do you mean by there's no zero divisor? Let's begin with a motivating example. Here we go. Here's a quadratic equation in Z. Yes, I can consider this equation in Q or R or even C, but in this case it's going to be okay. It turns out we only have integer solutions. Here we go. Factor the quadratic polynomial, and then please note that this is blue factor and that's green factor, and blue times green is 0, which means one of them has to be 0. Either blue is 0 or green is 0. From blue equation we get blue solution. From green equation, we get green solution, and there you go. We have two integer solutions. And I can do exactly the same thing in Q or R or even C. Let's come back to this. X can be any integer. So x minus 2 is an integer, x minus 3 is another integer. So what we have is integer times integer is 0. So one of them has to be 0. There's no way I'm going to get 0 by multiplying two non-zero integers. And you can use the same argument for Q or R or C. Multiply two real numbers. One of them has to be zeros. Complex number times another complex number is 0. One of them has to be 0. You see, you have all those kind of properties. Those are no zero divisor property. And as long as we have no zero divisor, you can do this factorization and you can set up for these kind of solutions. It works for Z, but not just in Z, but for Q or R or C and things like those. Now let's do the same thing for Z12. This is significantly different from Z or Q or R or C because this one has some zero divisors. Here we go. First solution here, which is a textbook's notation, and I prefer the bar notation. They're the same. Let's see. You can factor this polynomial into blue times green is equal to 0. And blue, well, you can plug in all the integer values here for x. So integer times integer is 0 modulo 12. And then 0 times anything is 0, so you can set up blue is equal to 0 or green is equal to 0. So from blue, we get blue solution, x equal to 2, same as before. And then from green, we have green solution, x equal to 3, same as before. If you use this bar notation, again the same thing, x bar minus 2 bar times x bar minus 3 bar is equal to 0 bar. And x bar can be any residue class. So this is residue class times residue class equal to 0 bar. And we're talking about a ring. Yeah, Z12 is a ring. So blue is 0 or green is 0 because 0 times anything is 0. So from blue we get blue solution 2 bar, and from green we get green solution 3 bar, same as before. But then again, please note that there are more. There are other ways to get 0 or 0 bar. I'm emphasizing these two, purple and brown. And x minus 2 is 4 and x minus 3 is 3 modulo 12. And that works for x equal to 6 modulo 12. So that 6 minus 2 is 4, 6 minus 3 is 3, and 4 times 3 is 12, but that's congruent to 0. Same here. 9 times 8 is 72, and that's 6 times 12, so that's congruent to 0. And that works for 11. 11 minus 2 is 9, 11 minus 3 is 8. In this expression down here, again, we can use the same color coding. Purple and brown. And then we have 6 bar purple or 11 bar brown. Are there any more? No, you can check manually, but there are no more. So, x minus 2 versus x minus 3. X minus 2 is 1 higher than x minus 3. So it has to be 4 times 3, not vice versa. You cannot have things like 2 times 6, for instance, because x minus 2 and x minus 3 must differ by 1, you see. So 4 times 3 or 9 times 8, there are no more. Anyway, we completely solved this equation in Z12. That's good news. But the bad news is we cannot use the same technique as before. There are zero divisors, so we have to consider those manually, case by case. So the solution became a heck of a lot more complicated. So, zero divisors sometimes cause trouble. And here's a precise definition of zero divisors. Let R be a ring. No non-zero elements, A and B, of R such that A times B is equal to 0 are called the zero divisors. A is a left zero divisor and B is a right zero divisor, respectively, because for integral domains, the multiplication is commutative, yes, but in general, the rings do not have to be commutative. So zero divisors may exist for non-commutative rings, and we're going to see those kind of examples shortly, actually. Let's look at such examples. First, determine all zero divisors of Z12, and that's a continuation from 1 to 1. In 1.1, we had Z12, right? And let's consider that. And here's the full list, actually. In this case, I do not have to worry about left zero divisors or right zero divisors because the multiplication here is commutative. And then it turns out, in case of Zm, all the residue classes given by integer between 0 and 12 that are not relatively prime to 12 will give me the zero divisor, actually. We're going to prove that later. So we have all these. And then, as a matter of fact, you can manually check everything. 2 times 6 is 0, 3 times 4 is 0, 3 times 8 is 0, and so on. I have every pair here. Okay, here's another example, this time non-commutative ring. A matrix ring, 2 by 2 matrices with integer entries, and then there are infinitely many elements, so we cannot check them all. Find just a pair. Well, here's an example. A times B is 0, and also B times A is 0, if you set like these. All good? Now here's my challenge. Find an example that A times B is 0, but B times A is not 0. You see, this ring is not commutative, so A times B and B times A are not the same. In this particular case, they're the same, they're both equal to 0, but in this case, no, they're different, and find such pair, A and B. Found it? Stop the playback and find it. Well, time's up. Here's my example, but there could be many more. A times B is 0, but B times A is not 0. Okay, all right. Those are zero divisors, and those are examples. Now, let's work out some theory associated to zero divisors. It turns out, zero divisors and cancellation laws are intimately related. The left and the right cancellation rules hold if and only if the left and the right zero divisors do not exist. Actually, it can be done separately. So the left cancellation law holds if and only if the left zero divisors do not exist. Okay? And then you're going to get the same thing about the right cancellation law. If and only if the right zero divisors do not exist. Yeah, you can do it like this. And then we're going to prove this one. And then for the second one, I'm going to leave that to you. I'll just do the left, and then the right part will be left as a homework for you. Okay. Okay, all right. This is a biconditional statement, so we have to prove two directions. First, suppose that the left cancellation law holds, and then it's going to be easy to prove the left zero divisor does not exist. What do you think? Is that easy to set up? Left cancellation law holds, suppose that, and then we want to prove that left zero divisor does not exist. Yeah, A times anything is 0 and A is not 0, then you can use A is not a zero divisor, so X has to be 0, you see? And establish that for arbitrary A, that means there's no left zero divisor, so that's going to be sufficient. Now, how do you fill this one in? How do you associate this left cancellation rule here? Try on your own. It's easy, actually. Got it? Well, here's the answer. Rewrite this into not just equal to 0, but A times 0 here. If I do that, A times X equals A times 0 like this, because A times 0 is 0. Now the left cancellation rule works. Cross out A, we get X equal to 0. You see? Suppose the left cancellation law holds, so you can cross out from the left. So here, I couldn't cross out right away, but if I have AX and A0, then yes, we can do that. Once you get the idea, it's pretty simple. So, if the left cancellation law holds, then there's no left zero divisor. We proved it. Now let's prove the other one. Suppose that the left zero divisor does not exist, and let's prove the left cancellation law. Let's set up left cancellation law like this. A times B is A times C, and cross out so that B is equal to C. And of course, A should be non-zero. That's the left cancellation law. All good? All right. And now your job is to fill this part in. Somehow you have to use the left zero divisor does not exist. How do you do that? Well, you have to use zero divisor, so you have to get 0. How to get 0? If you subtract that one to the other side, and then right hand side will be 0. Yeah, that's how it works. Here we go. Flip it over, then right hand side is 0, and then distributivity applies, factor A out. Now, there's no left zero divisor, so B minus C has to be 0. Consequently, B and C are the same. And what did you get? Yep, crossing A out, crossing A out. Yes, we got the left cancellation law. So, cancellation laws and then zero divisors go hand in hand.